Hello Chem students, this is another chapter 1 topic. This time we're going to talk about formal charge, just to assign numbers, positives, negatives, or neutral charges on atoms. In organic and biochemistry, when an atom doesn't have its normal number of bonds and lone pairs, it usually is in some more reactive state, usually less stable. And so we might see cations, anions, free radicals. And so you need to be able to classify what the atom status is in those situations. In organic and biochem, we generally use formal charge. You might remember in freshman chemistry using an alternative method called oxidation reduction numbers. But for us, we use formal charge. Okay, and so this will assign an atom's excess or deficiency of electron density, or if it has exactly the right amount, the neutral allocation. Okay, so it's just a bookkeeping scheme. So formal charge is going to occur or be calculated by using what an atom's Z effective is. So this is a constant number. For carbon, this would be +4. Nitrogen would be +5. Oxygen would be +6. Fluorine or halogens would be +7. And for hydrogen, this would be +1. And then we're going to compare that number, which is a positive number, to all of the negative electron credit, which is negative. If they come out exactly the same, there will be zero formal charge. However, if there's a deficiency of electrons, the positive number will be bigger and we'll get a positive formal charge. If there's an excess of electron credit, then the negative numbers will be bigger and we'll have a negative formal charge. Okay, so the atoms again that we see are hydrogen, carbon, nitrogen, oxygen, and we can approximate sulfur with oxygen. And then we're putting in fluorine, but fluorine could represent chlorine, bromine, or iodine, which we also use in organic chemistry. Okay, and here's the Z effectives that I just mentioned. They would be balanced by the normal electron credit that an atom has. And for each of these atoms, hydrogen makes 1 bond, carbon makes 4 bonds, nitrogen 3 bonds, and then it has a lone pair. Oxygen and sulfur, 2 bonds and 2 lone pairs. Halogens, 1 bond and 3 lone pairs. That's the normal status. So first rule of formal charge is when an atom's total valence electron credit exactly matches its Z effective, there is no formal charge. So these should be very familiar molecules to us. We have CH4, which is methane, and carbon has a Z effective at +4. And then if we count up all the electrons and bonds, that's 8 electrons. So if we come down here, we would have no lone pairs, but we would have 1/2 of those 8 electrons, which would be a -4, and overall it would be a 0 formal charge. If we went to nitrogen, this would be ammonia. Nitrogen has a +5 Z effective. Okay, it has 2 electrons in a lone pair, so it gets credit for both of those. And then 1/2 of the electrons in the bonds, there's 3 bonds, so 1/2 of those would be 3. So we get 5 - 5, 0 formal charge. And that's the way nitrogen will be when it has 3 bonds. For oxygen, oxygen makes 2 bonds and has 2 lone pairs. So if we come down and look at our little formula, oxygen has a Z effective at +6. It has 4 electrons in lone pairs for itself. It has 1/2 of the 4 electrons in the 2 bonds there, and that comes out to 6 - 6, or 0 formal charge. And we don't expect water to have formal charge. We never write it that way. And if we go to HF, the fluorine has a +7 Z effective. It has 6 electrons and 3 lone pairs that belong to the fluorine. It gets 1/2 of the electrons in the bond, so that would be 7. +7 - 7 would be 0 formal charge. These are all neutral molecules, should be fairly familiar to you, because carbon has its 4 bonds, 0 lone pairs, nitrogen's 3 bonds, 1 lone pair, oxygen 2 bonds and 2 lone pairs, halogens 1 bond and 3 lone pairs. So if the particular atoms are in this arrangement, then they will have 0 formal charge. The Z effective is balanced by the electron credit. Okay, so carbon can have 4 bonds, but it can do it with any of 3 hybridization states that we've studied. Okay, so here I have a carbon with 4 single bonds. Well, half of that would be 4 electrons. So it's 4 + 4 - 4 would have 0 formal charge. But if oxygen had a double bond, second pi bond here, the second bond, it would still have its 8 electrons. It would still have a 0 formal charge. And if there were 2 pi bonds between the carbons, so there were this would be sp hybridized, it's still going to have its credit for 4 electrons. Whoops. 4 electrons minus 4 electrons. 4 Z effective at plus 4 minus 4 electrons. 0 formal charge. If we come down to nitrogen, nitrogen's going to have 3 bonds and a lone pair. Well, it can do it with the 3 hybridization states that we've studied. sp3, there's no pi bonds, has its lone pair. Okay, this nitrogen is sp2. It has a second bond here, which is a pi bond using p orbitals and its lone pair. So this would be 0 formal charge, but sp2. This nitrogen has 2 extra bonds between here. Those would be pi bonds. So the hybridization would be sp, and the formal charge would be 0. If we look at oxygen, oxygen tends to make 2 bonds and 2 lone pairs. And so if we had single bonds, like in water, we would have 0 formal charge. And if we had a second double bond, a second bond here to oxygen, which would be sp2 here, oxygen still has its 2 lone pairs and half of the electrons in the bonds, so oxygen would still have a 0 formal charge. Okay, and halogens only make 1 bond, so we only expect them to normally be sp3, and we would have half of the electrons in this 1 bond, that would be 1, and then the 6 in the lone pairs, so that would be a plus 7, minus 7, 0 formal charge. Okay, so all of these atoms on this page here are 0 formal charge. So here I have a bunch of atoms with an unusual situation. They all have an extra lone pair. Okay, so normally carbon would have 4 bonds, but somehow we've lost one of these bonds, say a hydrogen, and we've retained the 2 electrons here. So what is the formal charge of something like that? Well, carbon has a plus 4 Z effective. It gets half the credit for these 6 electrons, that's 3 electrons, but it gets all of the credit for the lone pair, so that's 4, 5 electrons. So I have a plus 4 minus 5, and this would have a minus 1 formal charge. Over here, the carbon's normal, as we expect, 4 bonds, 0 formal charge. But here is exactly the same situation. You could do the calculation, or you could just recognize carbon has an extra lone pair that it normally would not have. So this is going to be a minus 1 formal charge. Here I have sp carbon, but all 4 bonds, so 0 formal charge. But on this end, you see again, I have an extra lone pair. So carbon's picking up an extra electron credit when we have this lone pair. Normally that would be shared, and carbon would only get half of those electrons. But here, we count them all. So this carbon has 5 electron credit. It would have a minus formal charge. If we come over here, this carbon looks almost identical. It would have a minus formal charge. On the other side, we haven't talked about the nitrogen, but the nitrogen would have a plus 5 Z effective. Gets half of these 3, that's 3, plus all of these 2, that's 2. So 5 minus 5 is 0 formal charge, just as we would expect for the nitrogen. Okay, the carbon here looks just like the previous 2 examples. We would expect a minus formal charge. On the other side, the oxygen looks a little bit different. Oxygen gets credit for half of these, that's 3 electrons, plus both of these, that's 5. Oxygen's Z effective is plus 6, minus 5, there would be a plus 1 formal charge. We'll see that a little bit later on. Okay, so you could go through and calculate all these. If we go through this list right here, we see nitrogen has an extra lone pair. Normally it has 1 lone pair, but here it has 2 lone pairs. So that's an extra electron credit. This would have a minus 1 formal charge. You could do the calculation. That would be 5, and then the electrons would be 4, 5, 6. 5 minus 6 would be a minus 1. Notice I have another extra lone pair, so this would be another minus. So instead of a minus 1 like we have over here, we would have a minus 2. And if I look at this, we have no bonds. All the electrons belong to the nitrogen. That's 8 electrons. Nitrogen's Z effective is plus 5 minus 8 would be a minus 3 on this guy here. Or you could just look and see we have 3 extra lone pairs. Okay, that would be a minus 3. For oxygen normally has 2 bonds, but you'll notice we have an extra lone pair. So that would tell us we have a minus charge on this for that extra lone pair. You could do the calculation. So oxygen would get these 6 plus half of this, that would be 7. Oxygen's Z effective is plus 6 minus its electron credit of 7 would be a minus 1. Here oxygen gets even another electron credit from an extra lone pair. And so this oxygen would have all 8 electrons and a -2 formal charge. Okay, fluorine in the same situation with all the electron credit only has a -1 formal charge because its Z effective is +7. 7 minus 8 would be a -1. Even hydrogen can be a minus charge. Hydrogen's Z effective is +1, but if it retains electron pair for itself, which we call hydride, then it would have +1 -2, it would have a -1. We would call that a duet instead of an octet. Okay, so every time you go from a bond where the electrons are shared to a lone pair where an atom gets full credit, you're going to pick up a -1 charge for that extra lone pair. Now this is a little bit different situation. The way I drew the structure here, this carbon looks just like it wants, 4 bonds, okay, 0 formal charge. This carbon has 4 bonds, 0 formal charge. This oxygen has 2 bonds and 2 lone pairs, 0 formal charge. But this carbon right here has 3 bonds and a lone pair. That extra lone pair is going to give it a -1 formal charge. Now because of the relationship with the pi bond, this particular situation has resonance, and the charge can spread over more than one atom. We'll talk about resonance in another little lecture that I give. But the electrons can be pushed in and shared between the carbons, so it would look like this, just a regular double bond, no formal charge. If we push the electrons onto this oxygen, and now it has an extra lone pair, and so the minus charge would be up here. So our problem is we can't draw a single structure that shows both of these atoms with their minus charge. We have to draw 2 different structures, and we use these arrows to show how the electrons move. The double-headed arrow in the middle means these are resonance structures. So together they show the actual structure. Resonance always spreads out electron density over more than one atom, and it does it in our course through 2p orbitals. This is always a good thing if you can spread out electron density. It's always going to be stabilizing. So these are the actual atoms again with their formal charge. So you see an extra lone pair minus, extra lone pair minus, extra lone pair minus, minus, extra lone pair minus. Loss of a lone pair, which we'll study in just a minute, is a plus. Extra lone pair minus, 2 extra lone pairs minus 2, 3 extra lone pairs minus 3. Extra lone pair minus, 2 extra lone pairs minus 2, 1 extra lone pair minus, 1 extra lone pair minus. These are all ways of making minus in organic chemistry and biochemistry, the most common way. Now in here we had the extra lone pair on the carbon. We pushed it in between the 2 carbons to make a pi bond and pushed these electrons onto the oxygen, and that gave the oxygen with the extra lone credit. So the minus in this structure right here is spread over the carbon and the oxygen together. Okay? Now there's another way we can make a minus charge in organic chemistry. This is not real common, but we do use it. Okay? And that is if an atom only had 3 bonds, say like boron and aluminum, they're in the same family, and their valence normal credit is 3 electrons, and they have a +3 Z effective. So that's their normal state. But to get to the octet, they can take on an extra pair of electrons. However, if I take on that extra pair of electrons, then I have a sigma bond for which the boron gets half credit. That's 1 electron. So that's 1 extra electron credit for the boron, and that would give it a minus charge. Aluminum is exactly the same, right underneath carbon in the periodic table. So if we added a hydride in here, the aluminum would have 1 extra electron credit and a minus charge. This is boryl hydride, which we will study later in the course, and this is aluminum hydride, which we will also study. Okay, they're very similar in chemistry. The aluminum is a little more reactive because it has a greater electronegativity difference, but otherwise pretty similar. Okay, so in this case, we went from an empty orbital, a 0, to a bond where we get half electron credit, so that's a -1 that we add to the structure. These are the only 2 examples that we'll look at in this manner here. Now, what about positive charge? So positive charge, again, there's 2 ways that we can look at it. Okay, one is very common for all of the other atoms except carbon. Okay, so the other atoms have lone pairs. Nitrogen, oxygen, the halogens, they all have a lone pair. And that lone pair could be bonded up with another atom, and I've chosen just hydrogen here to be nice and simple. So instead of nitrogen getting credit for a lone pair here, it gets credit for half of the electrons in the bond. that means it lost an electron credit. That means when I go to count up the electrons, I'm only going to get 4 electrons. Nitrogen has a +5 Z effective. I'm only subtracting 4, so 5 minus 4 is a +1. And nitrogen could be sp3, and this could happen, or nitrogen could be sp2, and still it's going to have a +1 because it only gets 4 electron credit. In this case right here, we could draw a resonance structure where we give these electrons back to the nitrogen. That means we steal them from the carbon, and so this is something we'll see in the next slide. Carbon only has 6 electron credit here. 4 minus 1/2 of 6, 4 minus 3 is +1. Over here, we're starting off with the carbon with less than 4 electron credit, so that's +1. In this case, I'm showing the nitrogen bringing in its electrons to help. So this is just 2 ways of looking at resonance, which again, that'll be a different topic in a little bit. Okay? So in this case over here, in the second resonance structure, the nitrogen only gets credit for 4 of electrons in the bonds. It has no lone pair for itself, and so that would give it a +1 formal charge. You'll notice in these structures, the plus is spread over more than one atom. That's what resonance is. Okay, so we're spreading out the electrons, in this case where we have a deficiency of electron density, as opposed to the last slide where we had an excess of electron density. Okay, so nitrogen you see is sp, sp2, and sp3 with a plus formal charge. Oxygen, you should be familiar with this one. This is H3O plus, even if you didn't know about formal charge. So notice we've taken away 1 electron credit for the oxygen, forced it to share with the hydrogen. So it lost 1 electron credit, has a plus charge. This is sp3. We could do that at sp2. Again, there's 3 bonds in a lone pair. So you see that we lost a lone pair, we're sharing. That's a loss of electron credit. Again, with the pi bond, we can move the electrons over to the oxygen, and now it looks just fine. 2 bonds and 2 lone pairs. However, we stole those electrons from the carbon. So carbon only gets half of the credit for these 6 electrons in the bond. So we would have 4 minus 3, that would be a +1. The true structure is the combination of these, and so we write them both to help us understand this kind of structure. Oxygen could even be sp hybridized if it has a plus charge. Because remember, if it's sp hybridized over here with these 3 bonds, the second and third bond would be p orbitals, so this would be sp. The electron, the formal charge would be from the +6 C effective of oxygen minus the 2 of the lone pair minus half of these 3 would be total up to 5. So 6 minus 5, oxygen would be plus. Okay, if we started off with the electrons missing from carbon, it would be the plus. And if we borrowed these electrons in to get to this second structure, then the oxygen would be plus. Okay? So again, oxygen could be sp3, sp2, or sp with a plus charge. Fluorine could also be plus, but normally fluorine would have 1 bond. So you see in this first structure, I've added an extra bond with an H, so I took away 1 electron credit that normally that lone pair would belong to the fluorine. That's sort of like the H3O plus up here. And fluorine could even have a double bond with a carbon. In that case, it would also have a plus. If I took these electrons back to the fluorine, it would be neutral as we expect, but then the carbon would lose that electron credit and be a plus. So once again, resonance shows how the positive charge is spread over more than 1 atom, or in the previous slide, how negative charge is spread over more than 1 atom. Okay? So in this case, we went from a lone pair that fully belonged to an atom, okay, and then we forced it to make a bond, so it got half credit. So the charge went to +1. Now there's another way we can make formal, before we do that, let's take a look at this. What is the hybridization of this carbon? So you might think about it just a moment. Look at that carbon. What is it? Is that sp, sp2, sp3, or no correct answer? Okay. So you might think, well, we just made an extra bond. That's what we were doing up here. So it must be like a +1, right? But then you think, carbon, does carbon have a lone pair? Carbon doesn't have a lone pair. We can't make an extra bond. This is a carbon with 5 bonds, which is not allowed in organic and biochemistry. So the answer would be no correct answer. Neutral carbon doesn't have any lone pairs. This is the way carbon makes a positive charge. Carbon usually has a group that it's willing to, the group that wants the electrons, electronegative, and willing to take those electrons away. Could be like a bromide or an iodide. Something that's real stable over here is a minus charge. But what that means for carbon is it lost one of its electron credits because it was shared here, and now it's no longer there. Now when you take those electrons away, the rest of the electrons expand so that their repulsion is minimized. And so this would become an empty 2p orbital, and this would become sp2 carbon. But the carbon has a plus charge. We call that a carbocation. Okay, carbo for carbon, cation for positive charge. There are other names that are used for this, but this is the one that we use. So remember, this empty orbital is a 2p orbital. Now it's even possible that carbon could start off at sp2 and lose a very good leaving group. This is much less common. But if that were the case, then these two groups would expand to linear shape to minimize their electron repulsion. The empty orbital is still a p orbital, plus there's the p orbital of the pi bond. Okay, so this would also be a carbocation, but we will hardly ever propose this, maybe never propose this. So in this case, we had a bond where the carbon got half of the credit, so 1 electron credit for its zero formal charge. But then when we took that electron away with this stable leaving group, then it lost that credit, and so it went to a plus 1. Okay, so that's another way that you can make positive charge. Now, the last rule that I have here is the total charge on the entire molecule, ion, or free radical is the sum of all the formal charges of the individual atoms. So as the example down here, I picked an amino acid. So this amino acid is called aspartic acid, something you need to eat every day. You'll notice there's the carboxylic acid group here, carboxylic acid group here. I have an amine, but the amine's protonated over here because that's the way it would be at a high acidity or low pH. So what is the overall formal charge? Well, if I go through here, 2 bonds, 2 lone pairs, 2 bonds, 2 lone pairs, 4 bonds, everybody looks okay except the nitrogen. The nitrogen has 4 bonds, and we know that that means it lost an electron credit, so we should have a plus charge there. Okay, so there it is. Now, if we come along and put in a base can take away one of these acidic protons. So let's show how that would occur. Oh, overall formal charge for the whole thing is plus 1. So if we took that proton off, left the electrons with the oxygen, we would have an oxygen over here with 6 electrons in lone pairs, and half of these, that would be 7 electrons. So that oxygen would have a plus 6, the effective, minus 7. This should have a minus 1 charge. We still have the plus 1 charge over here. Let's see, and now we have a minus 1 charge here. So overall, if we added this whole thing up, we'd have a plus and a minus. Overall, this would be a 0 formal charge for the entire structure. Now we still have an acidic proton down here, so it's possible we could take off this acidic proton with another base, and we would leave the electrons with the oxygen. So just as above up here, this should become a minus charge. So this still has too many bonds, 4 bonds. That should still be a plus. Nothing changed here, that should still be a minus, but now we should have another minus here. So if we add this whole thing up for the entire structure, the overall formal charge, these two charges cancel and we have a minus 1 on the overall structure. Okay, so we still have one acidic proton that could be removed. This is the last one that would be lost. And if we show that, we would pick up that proton and leave the electrons with the nitrogen. So now the nitrogen is exactly the way it wants to be. 3 bonds, 1 lone pair. But I have an excess charge on the oxygen and an excess charge on the oxygen. Okay, so looks like I lost my plus charge. I need to put that up there. Overall, we would have a minus 2 charge. Oh, I'm sorry, don't have a plus charge. I did it right. We would have a minus 2 formal charge on the entire molecule.